Hello, my name is Glenn Lipscomb. I'm a professor in the Chemical Engineering Department at the University of Toledo, and it's a great pleasure for me to give this virtual seminar on membrane process optimization for carbon dioxide capture. Before I begin, I want to thank Professor Hornbosel for the kind invitation. I'll talk about these three items. First, why, how, and where membrane processes have emerged. Then talk about some of the optimization studies that we've performed for one specific membrane process for CO2 capture. And then finally describe one of our broader impact activities. Membrane processes are capturing a growing share of the market for separations because they're cheaper. But why are they cheaper? Historically, separations have been performed using energy as a mass separating agent. So for example, in this distillation column here, energy is input into the reboiler to boil the liquid to produce a vapor that has a different composition than the liquid. And this allows us to perform the separation. Membranes are rate-based separation processes that can use a lower energy input chemical potential difference to perform a separation. We can do this if we can identify a material, the membrane, the blue line in the figure here, that allows preferential permeation of a particular species. So for example, if we have a mixture of green circles and red ovals, if we can identify a membrane that allows permeation of the green circles but hinders the permeation of the red ovals. If we identify a material like this, we can develop a process. Maintaining a chemical potential difference, for example, a pressure difference, across a membrane requires a lot less energy than boiling a liquid. The relative energy consumption of the dominant thermal separation processes, such as distillation and drying and evaporation, can be a factor of 5 to 10 greater than a membrane process. The energy consumption reduction that membranes afford comes at a cost though, and this cost is greater capital investment. And this is because the membranes themselves are more expensive and the process for making the equipment is more expensive. There are a number of success stories where membranes have displaced other separation processes. For example, desalination, where membranes have displaced, in large part, thermal processes such as multi-effect distillation and multi-stage flash. Nitrogen production from air, where membranes have displaced cryogenic distillation. Solvent nanofiltration is another application, as well as evaporative dehydration. All these processes have shared a common evolutionary history. And the history is illustrated here. The path begins with the discovery of a material that possesses interesting transport properties that will allow selective permeation when there's a chemical potential that's imposed across it. So membrane process evolution starts with this material discovery. And this is where the academic world is primarily involved in membrane process development. The decision whether to start commercialization typically is based on initial analysis of a separation process that utilizes that membrane. There's an initial process synthesis step, and based upon this, a decision would be made as to whether you want to proceed with commercialization. If the answer is yes, the next step is to make membranes and modules in sufficient quantity that you can actually create a pilot test of the process. This requires a substantial investment in capital and people. Now, upon commercialization, we actually have real-world use of the membrane process. You're going to find there's challenges that are associated with impurities, perhaps, in the feed fluctuations, and other factors that can arise. And you can develop potential pre-treatment and post-treatment processes that will address those. And that's the final stage of membrane evolution. I'd like to spend a little time talking about the nitrogen success story, where membranes are used to produce nitrogen from air. This membrane nitrogen industry did not exist prior to 1980, but has grown to be one of the dominant technologies, competing with PSA and distillation. The membranes are made into fine hollow fibers, as you see here. Commonly, the diameter is around 300 microns, the OD. These fibers are gathered together into a bundle, which is then placed inside a case, much like you put tubes into a shell and tube heat exchanger. Air is compressed and fed to the lumens of the fibers, where as it passes through the lumens, oxygen selectively permeates out. Other components like CO2 and water also will permeate out, leaving behind a nitrogen-enriched stream. This is our product. These modules can be put into a container or a crate and then moved to a point where nitrogen is needed. And as long as you have electricity, you can plug the unit in and produce nitrogen there. There's no need to deliver liquid. This slide illustrates what part of the nitrogen market that membranes occupied back in 1985. This was the time when the process had just first emerged. What's plotted here is the flow rate of the desired product, as well as the purity of the product in terms of nitrogen percent. At this time, the maximum purity you could produce with membranes economically was limited to around 99%. In fact, I think most people would argue is closer to 95%. If you wanted higher flow rates, regardless of the purity, then on-site PSA or on-site cryogenic liquid production was preferred, and at the lower flow rates, just delivered liquid was preferred. Over time, that portion of the market that membranes was competitive in did change. As you can see here, in 1991, it expanded to higher flow rates as well as higher purities. We continued to see an expansion to higher purities in 2000. And the last time this type of data was reported, back in 2012, you can see we maintained the purity from in 2000, but we expanded the flow rate range over which membranes were competitive. It's still the case that outside this region, at the higher flow rates, on-site PSA or on-site cryogenic liquid production is preferred, and at the lower flow rates, delivered liquid is preferred. What has enabled membranes to move and expand that share of the market that they're competitive in was manufacturing innovation. And so here's a patent that illustrates, I would say, is state-of-the-art in terms of membrane production and module production. The way membranes are made, the polymer in the form of a powder or flake is mixed with a solvent and then extruded to form a series of hollow filaments that eventually become the membrane. These typically pass through a gap, a gas-filled gap, most commonly air, and then into a liquid bath in which the structure is set. After this, the liquid and solvents are removed, the membrane is dried, and then in this particular case, these fibers are woven into a fabric which is wrapped around a mandrel to form the module. The tube sheets are formed by dunking the module into a bucket, essentially containing an epoxy resin that forms a tube sheet. The tube sheet is machined so that it has the right shape and fits into the module to produce the final object. Membrane processes for nitrogen production are in this phase here of the evolutionary process, in which there's great concern about how do you pretreat the compressed air to ensure that membranes have a longer lifetime. Of great concern is the oils that could potentially be in the compressor that will have an adverse effect on the membranes. For CO2 capture, membranes and membrane processes for CO2 capture were in this phase here, where manufacturers are just now starting to produce membranes and modules in sufficient quantity to do a large pilot test. Now let's turn to membranes and membrane processes for CO2 capture. Several strategies are being considered for capturing CO2 from the combustion byproducts produced at a fossil fuel power plant. The challenge is, how do you remove nitrogen from the feed air to the process? Well, there's some work been done to remove the nitrogen before combustion. There's been a significant amount of effort that's been put into removing nitrogen after combustion. And post-combustion processes using membranes are especially promising. Membrane processes are promising for economic reasons, but they're also promising for the ease of potentially retrofitting an existing plant. What's shown here are 3 systems for CO2 capture at the 20 ton per day level at the NCCC in Alabama. These 2 systems here, this advanced amine vendor as well as this pilot solvent test unit, make use of absorption technologies and different types of absorbents. The membrane system developed by Membrane Technology and Research is shown here, and you can see the dramatic difference in size between these 3 systems. So this might be an advantage if you're trying to put a membrane or a system for CO2 capture into an existing plant. The major barriers for post-combustion CO2 capture are shown here. First and foremost is the target of 90% recovery and 95% purity that has been set by DOE. Now, these specific targets might change with time based upon the development of technology, but these were the original values. Another factor is the low CO2 partial pressure driving force that exists in the stream as it leaves the boiler, and the potential large parasitic load that would be placed on the power plant by the capture system. And ideally, we'd like to see this capture occur with less than a 35% increase in the levelized cost of electricity. The key challenges for membranes are first trying to find a membrane material that's appropriate, a material that has a sufficiently high CO2 permeance and sufficiently high CO2 nitrogen selectivity. We want both of these to be as high as possible. If we make the permeance larger, we're able to reduce the amount of membrane that's needed, the area that's needed, and thus the associated capital cost. As we increase the selectivity, we'll reduce the electricity required, the compression required in order to perform the separation and reduce the operating cost. Once we have a material, then we have to decide upon how we're going to package that material and stage the membranes. And in each stage, we have to specify what would be the pressure we're going to operate, the pressures we're going to operate at. What should be the feed pressure, the high pressure that we're going to use, what should be the low pressure. We'll find that as we increase the feed pressure, we reduce the membrane area. If we can double the feed pressure, the absolute feed pressure, we can reduce the required membrane area by a factor of almost 2. Another factor is the stage cut. How much of the gas do we push across the membrane and collect as our permeate? The permeate is indeed the CO2 product that we're trying to recover and sequester. Finally, we're going to find that membranes by themselves are not quite capable of producing the desired purity and recovery. And so it's often found that membranes are used in a hybrid process, for instance, with a cryogenic condensation step, a liquefaction step that allows you to meet those targets. You can also combine this with other processes, absorption and adsorption. Previous studies of using membranes for CO2 capture have pointed out the fact that we do need sufficient feed compression to reduce the amount of membranes that are needed in order to achieve the right balance between capital and operating costs. We can also reduce operating costs by using a vacuum to help pull the CO2 across the membrane. Staging allows us to increase the CO2 feed partial pressure and thereby achieve the purity target. And finally, if we can use something like cryogenic polishing, liquefaction, that might be of benefit as well. What's shown here is the MTR process for CO2 capture. And we'll go through this in some detail. Let's start with where the gas leaves from the boiler. So this is the flue gas exiting. It will go through a first step where particulate matter is removed and then a desulfurization step before it will enter into the capture process. So it passes through a compressor and a cooler before it enters the first enriching stage, membrane stage. This is where the CO2 we're ultimately going to sequester will be produced. It will be permeate across the membrane and then go to a concentration step in which we'll achieve the purity required. Unfortunately, this first step is unable to meet the recovery target, the 90% recovery target. And so in order to remove the remaining CO2 in this stream, the air that's fed to the boiler is used as a sweep in the stripping stage here. So as the air flows through here, it will pull out enough CO2 that we're able to achieve the 90% recovery target. And in fact, the CO2 that we strip out in this stage and then recycle back as the feed to the boiler will have an increased CO2 concentration that will help enhance the performance of this enriching stage. Now, one of the drawbacks of using the feed air as a sweep in the stripping stage is that not only we'll take CO2 out of the flue gas, but we're going to lose a little bit of the oxygen that's in the feed air. So this stream that leaves here that we're going to use as the feed to the boiler, it will have a slightly higher CO2 concentration as well as a slightly lower oxygen concentration. And so there's concern about changing the composition of this feed air. And the preliminary studies that have been done to address this seem to indicate that if we keep the oxygen concentration at 18% or higher, is that it would be an acceptable feed for the boiler. Well, the CO2 that's produced or recovered in this enriching stage does not have sufficiently high purity in order to send it to sequestration in order to inject it. And so it goes through a second step to increase the purity. And this step here in the MTR process is a series of compressions and cooling stages in order to produce a stream that when we flash it will produce a liquid CO2 product of the desired purity. And this is what will go off to be stored. There is a byproduct produced from this liquefaction step, which can go through a membrane process as well to produce another stream that gets recycled back to the first enriching stage. We're going to focus on what types of membranes we would ideally put into these two stages right here, the enriching stage and the stripping stage. The ideal membrane material for the MTR process, or any membrane process, would possess an intrinsically high value for the ratio of the CO2 permeability to the nitrogen permeability, the selectivity, or alpha, and it will also possess an intrinsically high value for the CO2 permeability. We'd like to be in the upper right-hand corner of this plot right here. Well, Lloyd Robeson found many years ago in a seminal paper that is the most cited paper in the Journal of Membrane Science, is that if you scour the literature for reports of the CO2 to nitrogen selectivity as a function of the CO2 permeability for polymeric materials, is that all the data seems to lie below this line right here, a line referred to as the upper bound for performance. What this line indicates is that if you try to change the polymer structure in such a way that you increase the permeability, you go from left to right, is that you reach a point where you can no longer increase it at a given selectivity. Is that there's some limit that is intrinsic in the nature of the physics of permeation. Likewise, if you try to adjust, to tinker with the polymer material and to increase the selectivity while maintaining the permeability, is that you also encounter this line that you can't go above a limiting value for the selectivity. So although we like to be up in here, we know we're limited to lying somewhere along this line here or below it. So the question is, where should we be along this line? Should we be at the upper left-hand corner where we have a high selectivity and at the same time we have a low permeability, or should we be down here in the lower right-hand corner where we have a high permeability and a low selectivity? Well, what we're trading off as we move along this line here are operating costs versus capital cost. As we move along this line toward the upper left, what we're doing is that we see our operating costs decrease, but our capital costs increase. The operating costs decrease because the selectivity, as it increases, allows us to perform the separation more effectively. But as we increase the selectivity, we see our permeability go down, and that leads to an increase in the capital cost, the membrane area that's required. And likewise, as we move along the line toward the lower right-hand corner here, is that we have higher permeabilities, which reduces the area and the capital cost, but as our selectivity goes down, we have greater operating cost. So the question is, where should we lie along this line here? Well, the studies that we performed, here's a series of assumptions that we made to determine the economics in terms of the base cost of electricity and other costs associated with the economic analysis. Now, I'm not going to go into great detail regarding these. And for the initial set of optimization studies, we fixed the condensation conditions, the liquefaction conditions at a minus 25 degrees C temperature and a 25 bar pressure. And what's shown here is some preliminary results from the optimization study in which we varied the relative areas of the enriching stage and the stripping stage in the MTR process. We fixed everything else. We fixed the selectivity at 75, which is reflective of the material that MTR was using, and the feed pressure at 2 bar and the permeate pressure at 0.2 bar, which was also representative of the pressures they were considering operating at. So the figure over here on the left shows as a function of the stripping module area. That's the second stage here, in which we pull out enough CO2 in order to meet the recovery target. That's what's plotted on the x-axis. On the y-axis is the enriching module stage. This is a stage in which we produce the CO2, a concentrated CO2 stream that ultimately will lead to the liquid that we'll sequester. In this plot over here, the yellow lines here, the solid yellow lines, what they represent is the CO2 purity produced by the process. And if you look at the values here, they range from 0.98 down to 0.97. So in all cases, or 0.97, in all cases, we're able to meet the purity target of 95%. The dotted lines that you see running in this direction represent the recovery. And what you can see here is this dotted line right here represents 95% recovery, and this dotted line here represents 90% recovery. And so in order to meet the purity and recovery targets, we would need to use a combination of an enriching stage and a stripping stage that are in this region right here. That's to the right of this dashed line right here. Well, what is happening as we go from a very large stripping stage and a relatively small enriching stage along this line up to a very large enriching stage and a relatively small stripping stage? Where should we be? There's a large number of combinations here that allows us to meet our targets. And that's where looking at this plot over here to the right can help. What's plotted over here are three things. First is the CO2 recovery lines, which are these dashed lines right here, the 95% recovery, and this red line is the 90% recovery. That's the 90% recovery line corresponding to the 90% in the figure to the left. The other two lines on here are this dashed yellow line is the levelized cost of electricity with CO2 recovery at the 95% purity level and 90% recovery in terms of dollars per megawatt hour. And what you can see here is that as we move along this line at this end up here, the levelized cost of electricity is about $78 per megawatt hour. But as we move down from having a large enriching stage and a small stripping stage to the opposite, having a large stripping stage and a small enriching stage, is that the cost decreases to below $70 per megawatt hour. Well, we should operate here then in this region, shouldn't we? Well, remember that in the stripping stage, that we do capture the CO2 and meet the recovery targets, and we're able to reduce the cost of recovery, but we also lose oxygen in here. So the question is, how much oxygen do we lose along this line? And so the other line that's plotted on here, the other lines, these solid black lines, are the composition of the stream that leaves of our feed to the boiler, the composition of oxygen in that stream. And so if you have a very large enriching stage and a small stripping stage, the concentration is 20%. So it's nearly that of air. However, as you move along this line, what you see is that the composition drops to 19, 18, 17, and eventually as you get to this limit down here where you have a very large stripping and a small enriching stage, you're down to 15%. And this is not viable. So what would really determine where we want to be along this line is we want to be as far as possible toward the lower right here, but we're going to stop when we reach the limiting value for the oxygen concentration in the feed air to the boiler. So whether it be 18% or whether it be 19%. So it's a very interesting result about the relationship between the areas of these two stages. Before presenting the full optimization results, I want to talk about the effect of the intrinsic membrane transport properties on the economics, as well as our choice of operating pressures, a feed pressure and a permeate pressure on economics. First, we're going to talk about selectivity. Now remember, once we specify a CO2 nitrogen selectivity, we've also specified a CO2 permeability because we're moving along the upper bound. As we choose a higher value for the selectivity, we're also choosing a lower permeability for CO2. And what's plotted here is the levelized cost of electricity in dollars per megawatt hour as a function of the boiler feed air oxygen mole fraction. Now in the MTR process, we have these two membrane stages, the enriching stage and the stripping stage. As we change the relative area between the two, as we just saw in the previous slide, is that we're going to end up changing the composition of the feed air to the boiler because we're using the feed air to the boiler as a sweep in the stripping stage. As we increase the size of the stripping stage relative to the enriching stage, we're going to see a decrease in boiler feed air oxygen mole fraction. We're going to go from right to left here along the chart. So what this moving from a boiler feed air oxygen mole fraction of 0.2 to 0.14 reflects an increase in the size of the stripping stage. The results shown here are for a feed pressure of 2 bar and a permeate pressure of 0.2 bar. And for results are presented for 4 different selectivities from 100 down to 35. What you might expect is that the higher selectivity material would give us the lowest cost. Well, the opposite is true. The highest selectivity we considered here of 100 gave us the highest levelized cost of electricity. And as we decrease the selectivity, what we saw as we go from 100 to 75 is that we saw a decrease in the cost. As we went down further to 45, we saw a further decrease. But as we decreased from 45 down to 35, we saw an increase, a slight increase here. What this reflects is the trade-off between operating cost and capital cost. The higher selectivities give us lower operating costs but higher capital cost. And as we go down in selectivity, we're shifting that. So we have a lower capital cost and a little higher operating cost. And the optimum, given the economic parameters chosen, seems to be, in this case, we choose a value for the boiler feed air composition of around 16%. The optimum seems to be somewhere near 45. Now, one thing to note here is that you'll see that the results presented for the 35 selectivity membrane end at about a 17% oxygen mole fraction. And that's because we weren't able to achieve the targets, the target recovery, and the target purity without reducing the boiler feed air oxygen mole fraction to this point. So if you have a minimum composition of 19%, the 35 selectivity membrane would not give you that. Additionally, we couldn't get to 19% with the 45 selectivity membrane. Next, let's look at the effective operating pressures. And we're going to look at the same thing, levelized cost of electricity in dollars per megawatt hour as a function of the boiler feed air oxygen mole fraction. For, in this case, a fixed selectivity of 75. And so there's 4 sets of operating pressures that are shown here. The first 2 are for a feed pressure of 2 bar and 2 different permeate pressures, both vacuums. And then the second set are for a feed pressure of 4 bar and 2 different permeate pressures, both vacuums. And what we see is that the lowest levelized cost of electricity throughout the range of boiler feed air oxygen mole fractions is achieved with the higher feed pressure, which leads to a reduction in the capital cost because we're able to reduce the required membrane area, and a permeate pressure of half a bar. The results of the full optimization study are shown here. What you see are contours of constant values of levelized cost of electricity. And in each of these plots, what we've varied is the permeate pressure from 0.2 to 0.5 bar and the feed pressure from 2 to 7 bar for a fixed value of selectivity. So the first plot right here is for a selectivity of 45, the second is for a selectivity of 75, and the third 100. Now we determined the levelized cost of electricity for a fixed boiler feed air composition of 19%. We did deem this to be the lowest acceptable value going into the boiler. And what we see here is that as we vary the permeate pressure from 0.2 to 0.5 bar and the feed pressure from 2 to 7 bar, is that for a selectivity, membrane selectivity of 45, is that the lowest levelized cost of electricity is in this region here, and we reach a value of a little bit less than 72. Now, as we varied the permeate and feed pressure over these broad ranges here, we found that we weren't able to always satisfy the constraints in terms of keeping the boiler feed air oxygen composition at 19% and the recovery at 90%. And those points where we had problems achieving those constraints are illustrated with the arrows here. These are outside the minimum that we found. So within this region here where we did find the minimum, what we were able to satisfy all those constraints. As we go from a selectivity of 45 to 75, what we see is the minimum decreases slightly from 72 to 71.5, a little bit less than $71.5 per megawatt hour. As we increase the selectivity further from 75 to 100, we see an increase to 73, a little bit less than $73 per megawatt hour. So the optimum selectivity, if we use the same membrane in both stages, would be somewhere around 75. And we would use a feed pressure between 4 and 5 bar, and a permeate pressure between 0.5 and 0.35. Now we don't have to use the same membrane in both stages, and so the next slide illustrates what the results presented previously were for use of the same membrane material in both the enriching and stripping stages. What we're going to show now is the results if we allow those two selectivities to vary. What we found is that if we chose a selectivity for the enriching stage of 75 and the stripping stage of 45, we're able to achieve the absolute minimum levelized cost of electricity. And what we see here is that we can get down slightly below $70 per megawatt hour with a feed pressure between 3.5 and 4 bar, similar to what we saw previously, and a permeate pressure between 0.3 and 0.45 bar, similar to what we saw previously. Now, you might ask, well, you chose materials that lie along the upper bound. That upper bound is a line that we have seen move over the years. In fact, this line that you see here has been updated multiple times. But what if that's not true? Or what if we aren't able to find materials that lie along that upper bound? What is the effect of using materials that have poorer properties? And so what we did to examine that, we performed a sensitivity study in which we moved the upper bound to the left and then chose points along that line after we moved it to the left a certain percent. And the results of that sensitivity analysis are shown here in terms of increase in levelized cost of electricity, percent increase, as a function of the CO2 permeability ratio. So this is point over here, a 0% increase corresponds to using points along the upper bound, original upper bound. And as we move in this direction here, what we're doing is we're moving that curve to the left. And so this is the fractional value of the original CO2 permeability that we use in doing the calculation. So as we move, what this represents is reducing the CO2 permeability by 25%, 50%, and 75%. And what we see is that as we move the curve to the left, we see small changes in the levelized cost of electricity, small increases in levelized cost of electricity until we get to about a 50% reduction in the CO2 permeability. We saw the same thing whether we chose a selectivity for all the stages of 100 or we chose the optimum values for the selectivity of the enriching and stripping stages of 75 and 45. The results thus far have held the liquefaction step constant at the specified conditions. And now we're going to look at optimizing those conditions as well, the temperature and pressure at which we perform liquefaction. This slide illustrates the effect of changing the liquefaction pressure and temperature for fixed values of three different fixed values of the selectivity from 45 to 100 and fixed values of the feed and permeate pressure of 2 bar and 0.2 bar respectively. Now the contours here are not of levelized cost of electricity, but of percent increase in levelized cost of electricity relative to electricity production without CO2 capture. So this line right here, 40, represents a 40% increase in the cost of levelized cost of electricity. And what we see here is that there appears to be broad ranges of liquefaction pressures and temperatures that will produce the lowest increase in levelized cost of electricity. And the region is roughly the same regardless of the membrane selectivity, whether it is 45 or 100. This dot right here represents the conditions that MTR proposed in their preliminary process evaluation. The results of the full optimization study are shown here, in which we looked at the combined effects of the feed and permeate pressure on the increase in levelized cost of electricity, as well as membrane selectivity. We use the same membrane in both the enriching and stripping stages in this case, and the liquefaction conditions. The first number here represents the pressure, so the 50 here is 50 bar, and the second number represents the temperature. Minus 15 is minus 15 degrees centigrade. What we see is similar to what we saw before in terms of changing the selectivity. As we go from selectivity of 50 to 100, we see a minimum appear in the levelized cost of electricity or in the increase in the levelized cost of electricity relative to the base case. However, we see an optimum or minimum appear somewhere between 60 and 70 in terms of selectivity. For these two operating pressures, and as we change the feed pressure to 4 bar and the permeate pressure to half bar, we see there's a slight decrease in the minimum that we see, but the minimum still occurs at a membrane selectivity between 60 and 70. We also see that as we can reduce the levelized cost of electricity, the increase in it, by going to conditions in which we have a slightly lower pressure. And so the square symbols here represent a pressure of 15 bar and a slightly lower, or in this case, a significantly lower liquefaction temperature, in this case of minus 50 degrees centigrade. What we see here are the trade-offs between operating and capital costs. And so what's shown here is the energy requirement in terms of kilowatt hours per ton of CO2 captured for the cases we just looked at, for the two different operating pressures as a function of membrane selectivity, and for these 4 different choices of liquefaction conditions. As we increase the selectivity, what we see is that there is a reduction in the energy cost for both cases. But along with that reduction comes an increase in the required membrane area, which is an increase in the capital cost in both cases. And so these combined effects, the combined effect of an increase in capital cost that comes with an increase in selectivity, and that reduction in operating costs that leads to the minimum in the total levelized cost of electricity, or the increase in levelized cost of electricity. So just as a final note on membrane processes for CO2 capture, We're at this point in the evolutionary process where manufacturers now are making sufficient quantities of membrane and modules in order to do pilot testing, and we're eagerly looking forward to a much larger pilot test of the MTR technology in Norway in the coming year at the Test Center Mongstad. I'd like to end the seminar with a brief discussion of one of our broader impact activities. This is a joint program with the nonprofit Clean Water for the World and the Center for Exchange and Solidarity based in San Salvador, El Salvador. We started this program about 4 years ago. Clean Water for the World is devoted to improving access to safe drinking water in developing countries. One of the major problems that communities face in these countries is microbial contamination. In order to treat the water, what they have developed is the unit you see here. It's a UV light-based system that activates bacteria and viruses. Upon exposure to UV light, DNA can fuse. There's a chemical reaction that can occur between two base pairs. This covalent bonding of the DNA prevents it from separating and allowing the microorganisms to reproduce. Although the organisms are not killed, they're not able to reproduce if they're ingested. Over the past 4 years, we've taken 5 trips to El Salvador and Guatemala. 30+ students have participated in these trips. And during this time, we've installed 7 of these units that you see here is a picture of one of the students getting ready to install a unit. And we've maintained and serviced over 20 different units. This activity has evolved into a multi-year program. Students first get involved through a freshman design project that's part of our orientation class for chemical and environmental engineers. This class is taken their very first semester on campus. The design project asks students to evaluate the current UV system design and propose changes to it that might improve its effectiveness. One of the changes that was proposed and has been adopted is to replace the opaque blue cover that originally housed the filter that precedes the UV light chamber with a clear one. So it's easier to tell if the filter needs to be replaced. After they complete the design projects, students are given the opportunity to travel to El Salvador or Guatemala to install and maintain units. As sophomores, we hope that they continue by mentoring freshmen from the next year's class. As juniors, we encourage them to help write proposals to obtain funding for our trips and to get involved in their own research related to water treatment, either to improve the current UV system, develop an alternative UV system, or even propose a totally different way to treat water. And finally, as seniors, they can continue their involvement either through a capstone senior design project or an honors thesis. The current systems that are built and installed by Clean Water for the World are meant to be point of use systems, where a member of the community would go to the unit and withdraw water for their use, either to drink or to take home for cooking. What we found through Clean Water for the World is that there was a desire to treat all the water coming into a community and not just provide the clean water at one point. So 2 students undertook the design of a point of entry system for a community in Guatemala, which was the first time that Clean Water for the World had gotten involved in doing such a project. And these 2 students, these 2 young women you see over here, are Kylie Kramer and Allison Hawes. They undertook this project for their senior honors thesis. What you can see here is the completed project inside the structure that housed the water treatment systems here. And you can see 2 photos of the construction of the platform that was needed in order to install the photovoltaic array that we required in order to provide electricity to run the units. Unfortunately, we did not have access to an electrical line here, so we had to make this totally independent. This was quite a project. We spent a week in this community digging the holes to install the posts for the platform, installing the platform and the solar panels, and then installing all the parts that you see here, the UV chambers, the filters, the charge controllers, the batteries, and all the other stuff here. It was a great pleasure to see this thing all come to life after we installed it and turned it on and see it actually work. We've also had students get involved in designing a membrane system as an alternative to the UV system, and to design a UV system that uses LED UV light sources as opposed to the mercury-based fluorescent bulbs that are currently in the chambers that Clean Water for the World uses. There's other impacts that this has on students other than providing the engineering and design experience. When we take these trips, I think the students come back with a much greater awareness of the social and political aspects of water access. Water is something that is not as free and freely available in many parts of the world as it is here. Additionally, students come back with a much enhanced cultural awareness. We have interactions with students and with individuals in the local communities that we visit. So here's a picture showing a group of students after a soccer game that they had with some of the other students in the community there. And with that, I'd like to draw a few conclusions. First, I believe that membrane processes offer a viable option for CO2 capture. They are robust and affordable alternatives to meeting the DOE targets of 90% capture, production of a CO2 product of 95% purity, and doing so without increasing the levelized cost of electricity by more than 35%. Moreover, they offer unique opportunities for integration, retrofitting of existing power plants. And finally, I hope you saw the unique educational enrichment that was possible through our collaboration with Clean Water for the World. I know that there are multiple other opportunities for universities to work with nonprofits to do something similar. Finally, I'd like to thank Norfa Milici-Matt, the student that performed all the work that you saw here. She graduated a couple of years ago for a PhD. Her time here at the University of Toledo was funded by the Ministry of Higher Education in Malaysia. And with that, thank you for your time, and I look forward to hearing your comments and questions when I visit virtually on Tuesday.